In this section, we're going to start taking a look at being able to use more properties of integrals. Specifically, what we're going to do is we're going to take a look at utilizing definitions of even and odd to help us to evaluate special types of integrals. Right, so let's just review what it means to be an even function and what it means to be an odd function and the associated symmetry with those two functions. So let's start with an even function. An even function is symmetric about the y-axis. Right? And the most basic even function that I can think of is f of x equals x squared. And we know what f of x equals x squared looks like. It looks like this. Right? Now, let's say for some reason we're trying to find the area under the curve to some point A. All right, and this really isn't a good picture. Let me try again to get a little bit better picture of this parabola. There we go. That's a lot better. All right. And then we have its symmetric partner over here. And let's say that this, a point that would be equidistant from A, is going to be right here. So let's just assume this is negative A. Now, because this is an even function, we have this area, okay? So that, and let's just say right here is 0, all right? And we also have the exact same area right here. Right? So wouldn't it be suffice to say that if f of x is even, what we can say is that the integral from negative a to positive a of f of x dx is going to be equal to, well, we could just go ahead at 0 and go to a and then just double it, all right? Because that way we could just incorporate this part. So that would be two integrals of negative a, or I'm sorry, 0 to a, excuse me, of f of x dx. And why would we ever want to do that? Well, it might help us to be able to evaluate the integral because 0 is usually a nice number to plug in. So it might help us to be able to simplify that process. Okay, now that only works for an even function, right? Just a classification of a few functions that are even. Right? So we already said x squared, but x squared plus 3 is even. Right? Another even function would be something like x to the 60th plus x squared plus pi. Right? Notice that all of the exponents are even. And isn't it true that we could write 3 as x to the 0 power or pi as pi x to the 0 power? Right? So that would be like the coefficient. And clearly all the exponents are even. Right? There are some trig functions that are even as well. Right? So you might remember that the cosine function is an even function. Also, its reciprocal, the secant function, is also an even function. All right, so those are just some even functions. Right? Now, what about the properties for odd functions? And also, what does it mean for a function to be odd? So a function is odd if it is symmetric about the origin. All right. And let me give you an example of a function that's odd. In fact, probably the easiest function that's odd that I can think of is f of x equals x. And so if I were to graph this function, we would just have a line that goes right through the origin. Right? And let's say, similar to what we did before, we have a value a, and then we have another value, let's call that negative a, that's equidistant from a. Now, we notice that the area from 0 to a is the exact same area that's bound from negative a to 0, right? So, but the problem is that by that net change, or that net area, is this area is negative and this area is positive, and they're the exact same area, and so they should cancel each other out. when we try to go through and compute that. All right. And just as a really, really basic example of that, let's just say I went from -1 to 1. Let's just make this 2x dx. All right. Just to illustrate how this works very quickly, if we were to find the antiderivative of that, that would be 2x squared over 2 from -1 to 1, which is really just x squared. And then that's going to be 1 squared minus a -1 squared, which just becomes 1 minus 1, which is 0. And so that's what's happening, is that we have the positive area and then we have the negative area. Okay, so they cancel each other out. So the odd theorem suggests that if a function f of x is odd, what that means is that the integral from -a to a of f of x dx is just equal to 0. And just a review of some odd functions. As we said before, f of x equals x is an odd function. F of x is equal to x to the 55th plus x to the 7th is an odd function. This is not an odd function, by the way. If we had f of x is equal to x plus 1, anytime you have a constant, it automatically makes it not odd. Okay, so you might remember that from pre-calculus. Right? Trig functions that are odd: sine, cosecant, tangent, and then also cotangent. Right? So in calculus 2, when you start studying infinite series, you might see why they're called even functions and odd functions. All right, but for right now, because we don't know anything about infinite series yet, we're just kind of relegated to saying, well, a sine function is going to be odd because it demonstrates symmetry about the origin. All right, so hopefully this helps you to see these properties of even and odd, and also to kind of review what it means to be an even function and an odd function. And so in the next video, all we're going to do is just take a look at some applications as to how we could implement these properties and where they might be useful.